Hi everybody, we are the group 1, and today we are going to talk about the flip-flop fundamentals. Now what is a flip-flop?
Flip-flop is a small electronic circuit that can remember one bit of information, either a 1 on or a 0 off. It keeps its value until something tells it to change. It has two outputs. One shows the current value and the other shows the opposite. It's called bistable because it has two stable states, 1 or 0. Flip-flops are used in computers to store data like memory. You can build a flip-flop using simple logic gates like NAND or NOR.
Good day everyone. Today we're discussing one of the fundamental elements in digital electronics, the SR flip-flop or set reset flip-flop. Specifically, we're focusing on the clock or synchronous version of it, as shown in the diagram. So here, the circuit. On the screen, you can see a logic diagram with two NAND gates, forming the cross-coupled latch and two additional NAND gates receiving the S or set and R or reset inputs along with the clock or CP signal. This configuration ensures that the output changes only when the clock is high, making it a synchronous SR flip-flop. Okay. Next is the truth table. Here, the table inside the circuit lists all possible input combinations and the corresponding outputs, the QN, current state, and QN plus 1, next state. Okay, here the S, the input of S is 0, 0, 0, 0, 1, 1, 1, and the R is 0, 0, 1, 1, 0, 0, 1, and the QN is 0, 1, 0, 1, 0, 1, and X, and the QN plus 1 is 0, 1, 0, 0, 1, 1, and okay, the description or the final output is first is no change, and second is no change. The third one is reset, then reset, then set. Next is reset, then last is invalid. Okay. Note, when S equals R equals 1, the outputs become unpredictable due to both NAND gates being forced low, which breaks the stable feedback. So this is the invalid state. Then asynchronous inputs are PR and CLR. Below the truth table, you'll see your 4 specific cases involving PR or reset and CLR are clear. These are asynchronous controls, meaning they override the regular clock operations. Case 1, PR equals CLR equals 1. Normal operation, flip-flop responds to S, R, and CR. See converters. Case 1, PR equals CLR equals 1. Normal operation, flip-flop responds to S, R, and CP. Case 2, PR equals 0, CLR equals 1. Q is directly set to 1. Case 3, PR equals 1, CLR equals 0, Q is cleared, complement Q equals 1. Case 4, PR equals CLR equals 0, and valid state. Both set are reset and reinforced, which is not allowed.
Discuss about the SR flip-flop. In the flip-flop, with the help of reset and clear, when the power is switched on, the states of the circuit keeps on changing. That it is uncertain, it may come to set Q equals 1 or reset Q complement equals 0 state. In many applications, it is desired to initially set or reset the flip-flop, that is the initial state of the flip-flop that needs to be assigned. This thing is accomplished by the reset, which is the PR, and the clear, which is the CLR.
Let us move forward to GK flip-flop. What is GK flip-flop? A GK flip-flop is a type of digital circuit that stores a bit of information. So how does it store information? A GK flip-flop stores information in the form of binary digits, which are the 0 and 1. It has two stable states. The first one is the set state, or the Q equals 1, where the flip-flop stores a 1. The second one is the reset state, or the Q equals 0. The flip-flop stores a 0. So how does GK flip-flop works? The J input sets the output Q to 1, while the K input resets the output Q to 0. When both J and K are 0, the output remains in its current state. When both J and K are 1, the output toggles, meaning that if Q is 0, it becomes 1, and if Q is 1, it becomes 0. GK flip-flops are commonly used in digital counters, frequency dividers, and shift registers. They've also used in more complex digital systems, such as computers and telecommunications equipment. One advantage of GK flip-flops is that they can be used to implement more complex logic functions with fewer components. They're also relatively fast and reliable. GK flip-flops can be implemented using logic gates, such as NAND or NOR gates. The specific implementation will depend on the desired functionality and the type of gates being used.
Now let's move on to JK flip-flop truth table. So when clock is 0, no matter the value of J and K, there will be no change in output. As you can see above, 1 1 times 0 times 0, of course it's 0. But since we're using NAND gates, the output is 1. Now 1 times 1 is 1. Complement of 1 is 0. So the value of Q is 0. Now below, so there are 3 zeros. So 0 times 0 times 0, of course it's 0, but complement of 0 is 1. Now 1 times 0 is again 0, complement of 0 is 1. So the value of Q complement is 1. Now what if clock is 1? So there is no change in output since both J and K are zeros. Now what if we set J to 1? So since there are 3 1, 1 times 1 times 1 is of course 1, but complement of 1 is 0. So this will become 0, and 0 times 1 is 0, but complement of 0 is 1. So Q, the value of Q will become 1. Now that the value of Q has changed to 1, so as you can see, 1 times 1 is 1, complement of 1 is 0. So Q complement is now 0. So when we set J and the clock to 1, Q will become 1 and Q complement is 0. So now what if we set J to 0 and K to 1? Set K to 1. Now that there are 3 1s, the complement of 1 is 0. This value will become 0. And 0 times 1 is 0. Complement of 0 is 1. Now Q complement is now 1. It's now 1. Now that Q complement is 1, this will become 1. Now 1 times 0 times 1 is still 0. The complement of 0 is 1. This will become 1. 1 times 1 is the 1, but the complement of 1 is 0. Now the value of Q will become 0. So what happens is when we set K to 1 and J to 0, the output will reset Q back to 0 and Q complement to 1. So now what if we set both J and K to 1? Since there are 3 1 and complement of 1 is 0, this will become 0. And 0 times 1 is 0 and complement of 0 is 1. Now the value of Q will be 1. Now that the value of Q is changed to 1, so 1 times 1 is 0. So the value of Q complement is now 0. So now that both Q and Q complements change, J will be deactivated, K will be activated or will become high. Now since there are 3 1s complement of 1 is 0, and this will change q complement's value to 1. Zero, complement of 0 is 1, so this will change become 1, and 1 times 1 is 1, complement of 1 is 0, which will set the value of q to 0. So as what you might have noticed, that the value of q and q complement is going back and forth to q becoming 0 and q complement becoming 1, going back to q complement becoming 0 again and q becoming 1. So this is what is called a toggle, where q would toggle back to 1 and 0s and q complement toggling back to 0s and 1. And that would be all for JK flip-flop truth table. Thank you.
To answer, I'm which are on scope 1, and this is my part of 34. How did the stored and trigger in JK flip-flop? The JK flip-flop stored 1 bit of data, either 0 or 1. It maintains a state using feedback loops composed of interconnected logic gate.
So hello everyone, now I'll be explaining the faults of flip-flops, specifically their truth tables and timing diagrams, which show how the data is stored and triggered. So let's start with the truth table. So for example, in JK flip-flop, if J and K are both 0, the output stays the same. And if J is 1 and K is 0, the output becomes 1, and this is called the set. If J is 0 and K is 1, the output becomes 0, and it's called the reset. And lastly, if both J and K are 1, the output toggles, meaning it flips from 0 to 1 or from 1 to 0. So this behavior only happens when a clock signal is triggered, usually on the rising edge, or when the clock goes from 0 to 1. So now let's talk about the timing diagram. Timing diagram is like a graph that shows how the signals J, K, and the clock and the output Q change over time. So you can see when the clock signal goes high and the value at that exact point, based on the values of J and K, the output either changes or stays the same. So for example, if the clock rises and J equals 1, K equals 0, the output sets to 1. And if J is 0, K is 1, at the clock edge, it resets to 0. And if J is 1 and K is 1, so both the J and K is 1, the output toggles. The timing diagram helps us visualize exactly when the output changes and why. So let's conclude it. So basically, the truth table tells us what the flip-flop will do with certain inputs, and the timing diagram shows us when exactly it will do it. So in relation to time and the clock signal. So that's all. That's basically the fundamentals of flip-flops. To understand it more, the next group will tackle it. Thank you.